We will continue today's solution of problems on chapter 3. We have a tensile test. A tensile test uses a test specimen that has a gauge length of 50 millimeter and an area of 200 millimeter square. During the test, the specimen yields under a load of 98,000 Newton. The corresponding gauge length is 50.23 millimeter. This is the 0.2% yield point. The maximum load of 168,000 Newton is reached at a gauge length of 64.2 millimeter. First, determine the yield strength. Okay, so here they gave us the load at which the specimen will yield. So we have here the value of F, okay, and we know the area of the specimen. So all we have to do to find the yield strength is to divide the force by the area, because by definition, the yield strength is the force at which our specimen yields over A0, okay? And here, the force is in Newton, and A0 is in millimeter square. So what will be the unit of the strength? It will be in megapascal, okay? Because the Newton per meter square is Pascal. Newton per millimeter square is 10 to the power 6 Pascal. So it is, when you put directly the force in Newton and the area in millimeter square, you get the strength in megapascal. Now, the second question, find the modulus of elasticity. Whenever they tell you this is the 0.2% yield point, what they mean by this? When we did in the course material, we have seen that sometimes the yield point is not very clear on the figure. This is why we have a technique in order to determine the location of the yield point. So let us say we have this, okay? The 0.2% method is consists on the following. We take epsilon equal to 0.002 and we draw a line that is parallel to the, if you want the elastic slope, here you have a linear slope. So you draw a line parallel to it, and it will, here, the difference here is large, but in reality, it's a very small difference, okay? So it is very close, and 0.002 is very close to the origin. So this is the yield point. So whenever they tell you that this yield is calculated based on the 0.2% offset method, this means that what you should do to find the elasticity, okay, is the slope of this line. And how to find the slope of this line? The slope is delta sigma over delta epsilon. You know that E represents the slope. The modulus of elasticity is the slope of the line, okay? And it's equal to delta of sigma over delta of epsilon, okay? Now, since for delta of sigma, you have this point here. What is the characteristics of this point? It is characterized by epsilon equal to 0.02, but sigma equal to what? Sigma equal to 0, okay? So it's like you are saying that E is equal to the value of the yield strength minus 0 over epsilon of the specimen at this point, okay, minus 0.002, okay? So now Y already is calculated. Epsilon at this point, to find the corresponding epsilon here for the yield point, okay, we should see what was the length. They said that the corresponding gauge length at the yield point is 50.23 millimeters. So by applying the formula, how we calculate epsilon? Epsilon at yield point is 50.23 minus L0, which is 50, over 50. So this will give you epsilon at yield point. But now, since you want to do delta epsilon, you should subtract from it 0.002. And then to find E, you divide delta sigma by delta epsilon, you get your value in megapascal. Why? Because if delta sigma is in megapascal, and we know that epsilon does not have a unit, okay? So I get E in megapascal. Any question on this? Okay. Now, how to calculate the tensile strength? The tensile strength corresponds, to the maximum load. And they gave us the maximum load, it's given. And we have the area A0. Okay, so the tensile strength is simply the maximum load over A0. So here we just say that tensile strength is equal to F maximum over A0. And by replacing, we can get the value of the tensile strength. Then they ask if fracture occurs at a gauge length of 67.3 millimeter, determine the percent of elongation. So in order to determine the percent of elongation, I just apply the formula, which is L final minus L0 over L0. They gave me that L at this point, the percent elongation when we reach the highest value of maximum load is 64.2 millimeter. So the elongation at this point can be calculated as L at this location minus L0 over L0. So we get the value. Just 1 second, guys. Here, in general, the elongations, they ask for it at the fracture point, okay? They can ask you what is the value of epsilon at the maximum load, okay? But when they ask for the percent elongation, the percent elongation is for the final point. So I should take which length? I should take length at fracture, okay? Because when they say percent elongation, it is a representation of the ductility. It is the maximum, if you want, it represents the maximum the maximum value of epsilon, okay? So it is, I take the length at fracture, which is 67.3 minus L0 over L0. Now here, for example, this length, we didn't use it, 64.2. We will need it if they ask for epsilon for the engineering strain or the true strain at a value of the tensile strength when we reach the tensile strength. But since here they just want the percent elongation, we only consider the length at fracture, which is 67.3. So we can calculate based on this the value of elongation. And finally, the percentage of reduction in area. To find the percentage of reduction in area, we apply the formula, which is initial area minus final area over 200, okay? And concerning the final area is given, it's here. The next specimen area is 92 millimeter square at the final state. So we can just replace in the formula and we get the percentage of reduction in area. And both terms, percent elongation and area reduction, are representation of what? Of ductility. Okay, these both can be a measure of the ductility of the specimen. So higher is the elongation and the higher is the area reduction, higher is the ductility of our material. Any question on this problem?
No, doctor.
Okay, so let us continue. Problem 2 shows that true strain is equal. This part we did it last time. We demonstrated that true strain is related to engineering strain by the following formula. Now we will demonstrate the second part, that sigma true is equal to sigma engineering times 1 plus epsilon engineering. Okay. To demonstrate this, always go back to the definition. What is the definition of sigma? Sigma is the force applied on the specimen over A0, which is the cross-sectional area, the initial cross-sectional area, while sigma true is the applied force over the actual area. So if you do the ratio of sigma true over sigma, you get it's A0 over A. Now, since you want to relate here, you want to demonstrate that if you take sigma to the other side, you want to demonstrate that sigma true over sigma engineering equal to 1 plus epsilon engineering. So, and you know that epsilon engineering is function of the ratio L over L0. And we have demonstrated last time that 1 plus epsilon engineering is equal to L over L0. So what I will try to do now is to relate A0 over A to L over L0. And you know that from conservation of volume, A0 over A is inversely proportional to the ratio of length, because by conservation of volume, A times L equals to A0 times L0. And therefore, A0 over A is equal to L over L0, which is in turn equal to 1 plus epsilon engineering. So if I replace in the formula, I get that sigma true is equal to sigma engineering times 1 plus epsilon engineering. Now, one important remark, the conservation of volume is true, it's always applicable, but A times L equals to A0 times L0, it's only before necking. Because when you have necking, what will happen is that not all specimen will undergo the deformation and the reduction in area, but only the necked part will undergo a very high reduction in area. But this relation is applied, if you want, before the necking zone. Okay, because after the necking zone, it will be different. Now we use it for the whole values of after to calculate a true relation between true engineering and true strain. We apply it. Okay, we apply it for the whole curve, but you should know that physically it's only valid before the necking point. Okay. Now, another problem. The following force displacement data were collected during a tensile test in which the starting gauge length is 100 millimeter and the cross-sectional area is 150 millimeters square. So here they gave you the number of points from 1 to 6. You have the displacement in millimeter given for the different points and the force in kilonewton given for the different points. Okay. So the first step, they asked to plot the engineering stress strain curve. Before this, they gave us additional information. They said that the final data point occurred immediately prior to failure. So this is the final point of my curve. And yielding occurred at a load of 19.39 kilonewton based on the 0.2% of set value. So also they gave us the force of yield, and the maximum load is 29.42 kilonewton. Okay. Now, first we want to plot the engineering stress strain curve. In order to plot the engineering stress strain curve, we should use the formulas of engineering stress, which are sigma equal to force over the actual area. And here we know that the actual the initial area. The initial area is 150 millimeters square. Okay, and the force is given here in the table. So all you have to do in order to find the engineering stress is to divide each force at each point by the value n of the area. Now, if you keep the force in kilonewton and your area is in millimeter square, the value of sigma will be in gigapascal. Okay, and if you convert your force to Newton and you divide by the area, then you will get, in this case, the value of sigma in megapascal. Okay, so now first I will do the calculation. Okay, so here you have a table showing the calculation for the engineering stress F over A0. It will give you the following values. So here they kept F in kilonewton and A in millimeter square to get sigma n gigapascal. So you have here the value in gigapascal. In case you converted the force to Newton, you will get, for example, 118.6 at point 1, which is in megapascal in this case. Now, how to obtain the value of engineering strain? For engineering strain, we apply the formula of ln L, for the engineering strain, it's L minus L0 over L0. For the true strain, it is ln of L over L0. So now, since we want to plot the engineering curve, we will use the following formulas: F over A0 for sigma engineering, and for epsilon engineering, we have L minus L0 over L0. So this, by applying these formulas, we get the following table. And of course, to calculate L minus L0 over L0, you have here already they gave you the displacement. The displacement represents for each point the value of L minus L0. So already here, it's already calculated for you, L minus L0. So all you have to do to calculate the engineering strain is to divide L minus L0, which is the displacement, by the starting gauge length, which is 100. Then you will get the value of epsilon engineering. Okay? Now, the second step, in the second step, I will draw the curve. So once I have all points, so I do the calculation for the 6 points, and of course, I can obtain an additional point, which is 0, 0, because I start from 0. I will obtain the following curve. Okay? And as you can see here, you have nearly a flat region. This is why sometimes if I use the engineering curve, it's difficult to know exactly where is my maximum. I can find it as approximation, okay? But we will see together that when drawing the true curve and finding the separation point, I can find more exactly the value of the maximum load and the maximum stress. Here they gave me, in the problem, they gave me the maximum force applied, which is 29.42 kilonewton. Since it's given, I can easily calculate the tensile strength. Okay, but if they didn't give me this value, it is not easy. It's hard to see in the curve where is the maximum, because it's a flat plate, and maybe I have, I should have more points to be able to track the maximum in a more accurate way. This is why we will see that the truth curve will be more helpful to accurately determine the value of the maximum of the tensile strength. Okay?
Doctor?
So, yes?
The flow curve equation, it
Yes.
it only intersects the true curve ما هيك ما خاصة بالengineering curve.
Yes, ما خاصة بالengineering curve, because sigma the flow curve اللي هي k times sigma times epsilon to the power n. Epsilon in this formula is the true strain. Okay.
Okay, thank you.
This
Yes.
is why. Okay, so we draw it on the with the true curve, not with the engineering curve. Okay. Now, so the first step was to draw the engineering curve. Now, part B is to determine the yield strength. So here also they gave us the load at yield, which is 19.39 kilonewton. So we can simply divide by the original area A0 to get the yield strength. Now, concerning the modulus of elasticity, so also like the previous method, okay, since the yield value is based on 0.2 offset, so we will do as we did in the previous problem. We will consider E is equal to delta sigma over delta epsilon. So here we can see it here in calculation. So first for yield strength, we just say it is F at yield over A0 calculated. So here just you will add A0, it's the original area. And for the modulus of elasticity, we have that based on the offset methods of 0.002. Okay. Here, if you want, here in this case, I need a value for 1 point. I need to find delta sigma and delta epsilon. The value of what they did here for the modulus of elasticity, you can do it in two ways. Okay, you can use the method of offset, which is 0.2% method. Okay, Or also, and let us try to do both, okay? Or also you can say, since point 1 is in the elastic region, so I have a known point in the elastic region, and I know that my curve passed by the point 0, 0, okay? So here, as you can see, if you look at point 1 is in the elastic region. It's before yield, okay? Since I have 1 point before yield, then I can say, and I know that I start from 0, then for the modulus of elasticity, I can take the point 0 and this point. And then in this case, I can say that the value of E is sigma over epsilon, okay? So all I have to do in this case is to find the value of sigma at this point and the value of epsilon at this point. It's already done because I have calculated the values for epsilon and sigma at all points. So here, for this point, for this particular point, since these 2 points are in the elastic region, okay, and I can make sure they are in the elastic region because sigma at this point is smaller than sigma yield point. So this means that I didn't reach the yield point yet, okay? So I can calculate based on this, since these 2 points are on the linear part, so I can say that E can be calculated as sigma 1 minus sigma 0 over epsilon 1 minus epsilon 0. So I can say it is equal to 0.1186 over 0.002. And of course, then E will be in gigapascal. If I use sigma in gigapascal, E will be in gigapascal. Another method is to use the previous method in the first problem, okay? Because they gave me that this yield is at 2%. So if you try to do it, you will get very close values for the 2, okay? So here, since they have a point other than the yield, they use the point, okay? So you can just say that it is sigma 1 over epsilon 1, and you get the value of E in gigapascal. If you keep sigma in megapascal, the corresponding value هتكون in megapascal, بس هي times 10 to the power 3. فشيلوا times 10 to the power 3 and they put E directly in gigapascal. Okay, it is clear here what methods they use. So for E, for the elasticity modulus, you can take any point in the linear region. So if you have a point before the yield, if you know the characteristic of any point before yield point, you can calculate E. And if you want to use yield point and yield is based on the 2% offset method, you will use the method we used in the previous problem. Okay. As a practice, you can try to calculate E based on yield point, and you will see that you will get a very close result. Now, let us continue with questions. Okay, now we want to calculate the tensile strength and the percent of elongation. So these two also are very simple because we have, for the tensile strength, the maximum load is given. So we can just divide by A0. And for the percent of elongation, we consider always, as I said, when they ask about percent of elongation, so you should take the final point. So for the final point, you already have the displacement delta L. So all you have to do is to divide delta L by the initial length, which is 100. So you get that the percent of elongation is 35.1%. So here is the calculation. You have, for the tensile strength, I take the maximum force over A0. And for the elongation, percent elongation at fracture point, I take the displacement and I divide it by the original length. I get the percent of elongation. Now, part F, determine the strength coefficient and the strain hardening exponent in the flow curve equation. Whenever I have to find the strength coefficient and strain hardening exponent, what I should do is I should consider any 2 points in the strain hardening zone. What is the strain hardening zone? The strain hardening zone is between the elastic and necking zone. Okay, so first, if I look at my table here, okay, we have seen together that already this point is in the elastic region. So of course I cannot use it. Okay, now the yield point take place at which load? At 19.39. So yield is in between these 2 points. Okay, since yield is between these 2 points, I can be sure that any point after yield is in the strain hardening, but of course I should pay attention to be far from necking. So already I know that 6 is the fracture point. Okay, and of course I will not use 6. Okay, and for the tensile, for the maximum load is at 29.42. So it's nearly, it should be somewhere here. Okay, between 28.9 and 27.4. So the maximum the tensile strength is somewhere here. So this is why I will not take 0.5. I will consider that 0.5 is in the necking zone. I will not take it into consideration. Okay, because when I want to calculate properties for the flow curve, for the strain hardening zone, I should take points between elastic and necking zone, and just in between. I should never take a point in the elastic region and never take a point after necking. So here, the possibilities that I can take are points 2, 3, and in general, in the exam, if I just ask for to find these, just take 2 points, but make sure that the 2 points should be within the range. Okay. Now, if I ask you to calculate several times these coefficients and take an average, so if I specify this, then do it, because if you take several points, you will reduce the error. Okay. So for example, here you can take as couples 2 and 3, or 3 with 4, or 2 with 4. Okay, any 2 points will give you a system of 2 equations with 2 unknowns. Okay, which are, because you can write 2 equations, you know that these points should satisfy which equation? They should satisfy that sigma is equal to k times epsilon to the power n. Okay, so since these 2 points, any of these 2 points should follow this function, then their coordinates should satisfy the equation. Okay, so for example, here you will say that I will here this is the value of force, so you should go to the table of stress. Okay, and then you can apply. So here in this figure, you take the value of, and of course you will not take the table of sigma engineering. You should find which table now? You should find the table of sigma true. So you should calculate the value of sigma true in this case to be able to perform this operation. Okay, and calculate n and k. I cannot take sigma engineering. I should take true values. So here it's already posted here in this table. In this table, you have calculation of epsilon true and sigma true. So what you can do, based on the following formulas, sigma true equals sigma engineering times 1 plus epsilon engineering, and epsilon true equals to ln times 1 plus epsilon engineering. Since already you have engineering values, from engineering values, you can deduce the true values, epsilon true and sigma true, and you can arrange them in a table. And then say, here the points of interest will be these 3. So I can take as couples 2 with 3, or 2 with 4, or 3 with 4. Okay. And in this case, for example, if you select 2 and 3, for example, what will be your system? Your system will be sigma true at point 2, which is 0.15 8976 equals to k times what is the value of epsilon at point 2? It's 0.034401 to the power n, okay, and then we'll do the same for point 3. For point 3, I have that sigma true is 0.201626 equals to k times epsilon to the power n. Epsilon true is 0.099845 to the power n. Okay, and now first to find n, what can I do? I divide. So this is equation number 1 and this is equation number 2. If I do equation 2 over equation 1, I get that the ratio 0.201626 over 0.158976 is equal to, k will be simplified, okay, is equal to 0.099845 over 0.034401 to the power n. Okay, so in this equation, the only unknown is n. I can get the value of n. And once I get the value of n, I replace back into equation 1 or equation 2, I get the value of k. Okay, so in this way, I can solve for n and k. And of course, in this case, when you solve for n and k, if you repeat it for several points, you should have close values. So for example, this table is summarizing the calculation for several combinations. So for example, if I take 3 with 4, here this point, we have seen that it's better to so here you have I think here they mean not 5, they mean 2. I think maybe it's an error in typing. Okay, so if you take several combinations of points, you will end up with very close values. So for n, for example, you get these 3 which are very close to each other. Okay, so n is 0.2231 and k is 0. In average, so all are very close. And you can take any of these 2 points, you will get exactly close result. Here just I want to tell you that here in the table they are counting points from 0, 0, 1, 2, 3. Here they are counting points from 1 to 7. And here if you want, this represent combination of, in the table down, this represent combination of 2 and 3. Points 2 and 3, and this is point 2 and 4. Okay, and this is point 3 and 4. Okay, because just they are here. I enumerate the numbers from 1 to 7, and in the table down it's enumerated from 0 to 6. That's it. Okay, but 5, يعني هذا الpoint in the other table is 6 because they are counting here from 1. This is the only difference, okay? But you cannot take 0.5 in the calculation because it is not in the zone. You should take 2, 3, and 4, okay? So as you can see, whatever combination I take, I will get close result. Now, if you try to take with 5, you will see that you will start to have a difference, okay? The difference maybe at 5 will not be very high, but it is still a difference. So it is more accurate to take 2, 3, and 4. Or 2 with 3, or 2 with 4, or 3 with 4, and then you will get accurate results. So this is about calculating the strain hardening exponent and the strength coefficient. And of course here n is without unit, and k will have the same unit as sigma. So if sigma true is in gigapascal, the value of k you obtain will be in gigapascal. Now, draw the true stress strain curve and compare true and engineering stresses. So in order to draw the curve, it's very simple. Already we should construct the table using the formulas. So here, once we have the table of epsilon and sigma true for the different points, all we have to do is to plot is to plot this curve, and we can obtain then, it's here, I think, yes. Here you can see that the profile of true stress is different than the profile of engineering graph. But if you want to compare them on the same graph, you should have common axis here. And since sigma, the engineering curve is drawn function of sigma engineering, and the true curve is drawn function of epsilon true, if you want to compare them on the same graph, you should take something in common between the two. What is common between the two is the length of the specimen. Okay, so at any length of specimen, I can calculate sigma engineering and sigma true. So or L, or you can take also delta L. Yani the only difference between the two هي minus L0. Yani it is as a scale, it will be the same, just the difference is a number which is L0. So here, to be able to compare the curves, we can draw the two curves on the same graph, function of length of specimen. In this way, you will be able to compare the difference in values. And as you can see, as expected, in a tensile test, the true stress values are higher than the engineering value. And also, you can see the variation in profile. Engineering curve, you nearly have a flat plate that, for this reason, it's difficult to find a maximum. While for the true curve, it's a little bit easier to identify a maximum. But even if you want to find in a accurate way the necking start, the best thing to do is to draw on the same curve the flow curve and the true curve, which we will do now, and look at the location of the separation point. Okay, so now in the next step, they asked us in the final question, they said determine the necking point graphically and calculate again the tensile stress. Okay, so if you want to determine graphically the necking point position, what we should do now, we should draw both the flow curve and the true curve, okay, on function of the true strain, because you know that the flow curve equation is function of epsilon true. Okay, so to be able to compare them, both should be drawn function of epsilon true, and this is what we will do here. We already have the values, the table of values for sigma true, epsilon true. It is already here. We have calculated based on the following formula. So since we have already found epsilon engineering, sigma engineering, we have calculated sigma true, epsilon true, and the values are already summarized in the following table. Now what we should do, we should add a line, which is sigma flow, okay, for the flow curve, sigma f. And how to find the values for sigma f? What should we do? How to calculate the value for sigma f? Who will tell me? The flow curve is defined by what? What is the flow curve? So it seems you didn't start to study.
Sigma is equal to K epsilon,
K epsilon
exponent n.
lower n. Okay, so already, and epsilon, of course, epsilon true. Okay, already we have calculated K and n in the previous step. Okay, so we can take the average value since we have considered several combination of points. Then we take the average value for K and n, and we replace them in this formula to find sigma flow for the different points from point 0 to point 6. Okay, of course, if you want for point 0 and 1, there is no meaning for the flow curve, because mainly the flow curve represents the strain hardening behavior. So no need, you can find values at 0 and 1, but you will have deviation between the flow curve and the true curve for the elastic region. They will not be